Okay, let's unpack this. For weeks now, we've been swimming in the deep end of theoretical computation, really focusing on that one ultimate question. Is this problem solvable or is it not?
Right.
And we've set up these two big pillars. On one side, the decidable problems, where we can absolutely guarantee a yes or no answer in some finite amount of time.
Even if it's a ridiculously long time.
Exactly. And on the other side, the truly undecidable with the halting problem as our ultimate benchmark for impossibility.
But the thing is, unsolvable isn't really just one big monolithic category. That's the key idea for today.
It's not so black and white.
Not at all. If you think of solvability as a spectrum, we've really only been looking at the absolute endpoints. Perfect, solvable black, and this sort of ultimate total gray of undecidability. Today, we're exploring the nuance within that gray area.
We're venturing into semi-decidability.
Exactly. It's a degree of impossibility where somehow we can still find a path to certainty, but only if the answer happens to be positive.
And that's the mission for this deep dive, isn't it? To figure out how we can algorithmically tell the difference between a program that definitively says no and one that just runs forever, offers nothing but silence.
It is. And for you listening, understanding this boundary, it really changes everything about how you view what a computer can and cannot do.
Okay, so before we jump in, let's do a quick toolkit check, a little recalibration of the core concepts.
Good idea. You really need two tools ready to go. The first is, of course, decidability.
Right. A problem is decidable if an algorithm, a Turing machine, always, and I mean always, halts. It finishes its job and gives you a clear one for yes or a 0 for no.
Think about checking if a propositional logic formula is satisfiable. The SAT problem. We have algorithms for that. They might be slow, they might take exponential time, but they're guaranteed to stop and give you an answer.
That certainty is the absolute key. I know I will get an answer. The machine must stop.
Precisely. And the second tool, maybe the most powerful technique in all of theoretical computer science, is reduction. We have to see reduction as this incredibly versatile mechanism.
Right, it's like a universal adapter. On one hand, you use it to prove things are solvable. You get a new problem, let's call it A, and you figure out a way to translate it into a problem B that you already know how to solve. If that translation works, A must be solvable too. You're sort of transferring the certainty.
And then you flip it on its head. Reduction becomes this powerful weapon for proving impossibility.
This is where you connect your new problem A to that great wall of impossibility, the halting problem.
Exactly. If you can show that solving your problem A would magically give you a way to solve HLT, which we know is impossible, then A must be impossible too. It's a beautiful proof by contradiction.
So we have the boundaries, the decidable class, REC, and the impossible class. Now let's dive into that middle ground, the nuance. Let's talk about semi-decidability.
It sounds like some academic compromise, doesn't it?
It really does.
But it's computationally precise. And it's actually the most common compromise we encounter. When a problem is undecidable, it doesn't mean we're just completely helpless.
It just means we can't guarantee an answer for all inputs.
Exactly. And there's this entire massive class of these problems, the semi-decidable ones, where we can still algorithmically recognize the positive answer. We can find the yes whenever it exists.
Okay, so let me get this straight. If the answer is yes, the algorithm shouts yes and stops.
Right.
But if the answer is no, the algorithm is allowed to. What? Fail spectacularly. Just run forever without any consequence for the definition.
That is the exact trade-off. Let's formalize it for a second. For a decidable set, we have what's called a characteristic function, G. If an input is in the set, the function returns 1. If it's not, it returns 0. It's a total function. It's defined for every single input.
That function is the machine that always halts and gives a clear answer.
Right. Now, for semi-decidability, we introduce the semi-characteristic function. Let's call it chi prime. This function is what defines a set as semi-decidable.
And how is it different?
It's different in one critical way. If the input is in the set, the yes case, the function returns 1. Perfect. Same as before.
Yeah.
But if the input is not in the set, the no case, the result is formally defined as not defined.
Not defined. And that's where the silence lives. My program is allowed to crash, or I guess more commonly, just enter an endless loop. It has no obligation to spit out a 0.
That is the critical distinction. It is allowed to just silence. On a Turing machine, this means the machine just never enters a halting state. It keeps calculating, keeps moving its tape, maybe gets stuck in a little two-state loop forever. The key is that the absence of a result is what signals no.
But hold on, doesn't that make the algorithm kind of useless in practice? I mean, if I run my program and it's been silent for 5 minutes or an hour, can I just set a time limit and call it a no? Why is that so different from true decidability?
That's an excellent question, and it gets right to the theoretical power of this definition. If you set a time limit, say 1 hour, you're only performing a limited search. If the machine halts in 59 minutes, great, you found your yes. But if it's still running at the 1 hour mark, you can only say the answer isn't yes within this 1 hour window. You can't definitively say the answer is no for all time.
Because it might have halted at 1 hour and 1 second.
It might have. A truly decidable problem has a procedure that guarantees it will stop, even if it takes a billion years. For a semi-decidable problem, the search for that no is potentially infinite. Setting a hard time limit means you risk being wrong. The formal definition demands that recognizing yes has to be certain whenever it happens.
So the ability to return a 1 is finite and guaranteed if it exists, but the absence of a 1 is potentially infinite and uncertain.
You've got it. That philosophical difference is what helps us set realistic expectations, especially when you're searching through, well, infinite possibilities. We can recognize the existence of something like a proof or a terminating state, but we can't definitively prove its non-existence.
Okay, let's make this concrete. Let's apply this distinction immediately to our favorite problem, the halting problem, HALT.
Perfect example.
We know we can't build a universal machine that always tells us if another machine M will halt on some input W. It's the definition of undecidable. But is it semi-decidable?
It is. And the procedure to prove that HALT is semi-decidable is maybe the most elegant demonstration of this whole concept.
Okay, let's unpack this. Walk us through the procedure, step by step.
The procedure is beautifully simple. Simulation. We build a specialized Turing machine, let's call it an H-prime machine, that acts as a universal interpreter or a simulator.
So it takes two inputs. The code for the machine M we want to test and the input W for that machine.
Exactly. And H-prime does only one thing. It simulates M running on W step by step, exactly as M would run in the real world. It updates the tape, checks the state transitions, it just mirrors the entire calculation.
The simulator is like a digital shadow of the machine it's testing.
That's a great way to put it. Now, we just watched for the yes case. If eventually after 10 steps, or 1,000 or 50 billion steps, the simulated machine M enters its halting state.
Our simulator H prime sees that happen.
It sees it immediately, and at that exact moment, H prime stops everything and outputs a 1. We've successfully found the positive instance. The pair, MW, is in the set HALT.
That makes the yes side perfectly accessible. Termination is a finite, recognizable event. It might take an eternity, but it happens in a finite number of steps.
And now for the other side, the no case. What if machine M is designed to enter an endless loop?
Then the simulation just runs forever.
Exactly. If M never terminates, our simulation H prime runs eternally right alongside it. It never produces an output. It just keeps churning, forever looking for an endpoint that doesn't exist. The result is not defined.
Which perfectly fulfills the requirement for this semi-characteristic function.
Perfectly. We can recognize termination when it happens, but we simply cannot algorithmically recognize non-termination.
So this is why debugging code that seems to be stuck in a loop is so frustrating. You're literally facing this undecidability barrier. You can see it stop, but you can never know for sure that it will never stop.
That's the practical consequence of the theory. It means we can build tools to verify successful termination, but we can't build general-purpose tools to prove non-termination. That other problem, the complement of HALT, that's what lies truly outside this semi-decidable area. We'll definitely get to that later.
Okay, so the moment we've established this for HALT, the rest of the semi-decidable landscape just opens up, right? Thanks to our powerful tool, reduction.
Indeed. We use the lemma from our source material that directly links reducibility to semi-decidability. If you can reduce problem A to problem B, and you already know that B is semi-decidable,
then A has to be semi-decidable too.
It's an incredibly efficient way to classify problems. Once we have ALT as our anchor, we don't have to build these complex simulation procedures from scratch every single time.
Let's take the special halting problem, SHALT. The question is just whether a machine halts on the empty input.
Right. We already know SHALT is undecidable because it's reducible from HALT. But by the same logic, since SHALT reduces to HALT and HALT is semi-decidable, then SHALT must also be semi-decidable.
And the translation is simple. You just build a little wrapper program that ignores its real input and forces M to run on an empty tape. Then you feed that whole package into our HALT semi-decider.
Trivial. And now we can expand our scope way beyond Turing machines and see just how common this principle is.
We're basically looking for any problem that involves searching through an infinite but countable set of possibilities.
A classic example comes from formal logic, the validity problem in first-order predicate logic. We call it VALFO.
The question here is a given logical formula universally valid? Is it a tautology? Is it true under every single possible interpretation?
Exactly.
Why is this semi-decidable? It doesn't immediately feel like a simulation problem.
It's not about simulating a machine, it's about searching for a proof. The whole idea relies on using a formal proof system, like the sequence calculus, which has two vital properties. First, it's correct. Anything you can prove is genuinely valid.
Okay, that's important.
But second, and this is the critical part, it's complete. That means every valid formula has a proof within the system.
Ah, that completeness part is the linchpin for semi-decidability. If a proof exists, the system guarantees we can generate it somehow.
Yes. And since the set of all possible proofs is countable, we can list out every possible string of symbols and check if it's a valid proof. We can build a semi-decider based on that search.
So the procedure is just enumerate all possible proofs.
It's that elegant. Systematically generate every possible proof string. Check proof 1, then proof 2, then proof 3, and so on in an infinite sequence. If the formula you're testing is valid, completeness guarantees its proof is somewhere in that list.
And when you hit that proof,
you recognize it, you shout, yes, and you halt.
But if the formula isn't valid, if no proof for it exists, then you enter that familiar computational twilight zone.
Precisely. The search continues forever. You never stop looking, because you can never be certain that the very next proof you generate won't be the one. It's the exact same infinite silence we saw with the halting problem.
Okay, let's try a less abstract example, the one that's always described with dominoes, the post-correspondence problem, or PCP.
Ah, yes. PCP is a fantastic example. It's a foundational, undecidable problem, but it feels more like a puzzle.
So you're given a set of tiles, right? And each tile has a string on the top and a string on the bottom.
Correct. And the goal is to find a sequence of these tiles. You can reuse tiles so that the string you get by concatenating all the top halves is exactly the same as the string from all the bottom halves.
So if I find a sequence of tiles that creates a match, I've found a solution.
You have. And since the sequence of tiles can be arbitrarily long, the set of all possible sequences is countably infinite.
Sequences of length 1, then length 2, then length 3.
And so on. So the problem is semi-decidable. Our semi-decider just systematically tries every possible sequence. It checks all combinations of length 1, no match. Fine. It checks all combinations of length 2, no match. Length 3. Just keeps going.
And if a solution exists, no matter how long the sequence, we're guaranteed to find it eventually and halt with yes.
But if no solution exists, we search forever. It perfectly illustrates why searching an infinite space for a finite object leads to semi-decidability. The yes is finite and recognizable. The no requires infinite exploration.
And we can even build on this. What about the unsatisfiability problem in predicate logic? Given a formula, is it unsatisfiable? Can it not be made true under any interpretation?
You might think that's a no statement. It sounds like it should be in the complement class.
It does, yeah.
But we can cleverly reduce it back to the yes class of VALFO. We use a standard logical equivalence. A formula phi is unsatisfiable if, and only if, its negation, not phi, is universally valid.
Oh, that makes sense. If there is absolutely no way to make phi true, then it must be that every possible way makes not phi true.
Exactly. So our reduction just takes the input phi, sticks a not symbol in front of it, and feeds that new formula not phi into the VLFO semi-decider we just described.
So if phi is unsatisfiable, then not phi is valid. We'll find its proof, and we say yes.
And if phi is satisfiable, then not phi is not universally valid, and our proof search runs forever. Again, we can recognize the positive existence of the property, in this case, unsatisfiability, but not its absence.
This is great. We've defined semi-decidability, and we've seen it in action with these huge problems like HLT, proof validity, PCP. Now we get to what you called the most elegant theoretical connection in this entire field.
Yes, the link between recognizing a solution and actually listing out all the solutions.
This is where we connect recognition with generation.
It's formalized by a really important theorem, the equivalence theorem. It states that a set is semi-decidable if and only if it is recursively enumerable.
Two different names for the same fundamental property.
They're two sides of the same coin. The ability to recognize something if you see it is equivalent to the ability to generate a list of all possible examples of that thing.
Okay, one direction seems pretty easy. If I can list out all the elements of a set, if it's enumerable, then building a semi-decider is simple. To check if my input word W is in the set, I just start the list generating. If one ever appears, I shout yes and stop.
That's the easy direction. The challenging and much more profound direction is the reverse, showing that if a set is semi-decidable, meaning we have a machine that can recognize the yes case, we can then construct a function that enumerates all the members of that set without ever getting stuck.
And this is where the naive approach fails spectacularly.
It fails immediately. Let's set it up. We have our semi-decider machine M, and we have a list of every possible input word in existence, W0, W1, W2, and so on.
If I try to build my listing function naively, I'd say, okay, function, test W0. So it runs M on W0. If it accepts, great, add W0 to my list and move on to W1.
But what if W0 is not in the set?
Then M runs forever on W0, and my listing function gets permanently stuck waiting for it to finish. It's trapped. It never gets to W1, W2, or anything else, even if all of those are in the set.
Exactly. A proper mathematical function has to be total. It must produce an output. This naive approach fails because it starves all other computations.
Here's where it gets really interesting. This seems like an impossible hurdle. How do you structure a computation so that no single infinite loop can bring the entire process to a grinding halt? How do you run potentially infinite simulations in parallel?
The answer is the absolute genius of dovetailing, sometimes called the zigzag method. It's a technique designed specifically to transform a sequential process into a parallel one in a countable way.
The trick is to stop any one task from monopolizing all the time.
Right. Let's visualize it with that two-dimensional grid. Imagine a huge grid. The horizontal axis is all our possible input words, W0, W1, W2, off to infinity.
Okay.
The vertical axis is the number of computation steps, or time, step 0, step 1, step 2, going down forever.
If we just go down the first column for W0, we might never finish.
Right, that's the naive approach. That path leads to starvation. Dovetailing uses a diagonal path. It zigzags across the grid, a bit like Cantor's pairing function. Every point on that grid represents simulating a specific word for a specific number of steps. By moving diagonally, we guarantee that we visit every single combination of word and time in a finite ordered sequence.
Can you walk me through the first few steps?
Sure. In phase 1, we do 1 step of computation on W0.
Okay.
In phase 2, we do 2 steps on W0 and 1 step on W1.
Ah, I see.
In phase 3, it's 3 steps on W0, 2 on W1, and 1 on W2. We're allocating increasing amounts of time to an increasing number of words all at the same time.
So this guarantees that if some word, say 100, needs 5 million steps to be accepted,
we will eventually reach the coordinate, 105 million steps, on our diagonal sweep.
And at that exact moment, we'll detect its acceptance. It doesn't matter how far down the list the word is or how long it takes. Dovetailing guarantees we will eventually get there.
That is the crucial insight. We have replaced an infinite sequential search with an infinite yet countable and manageable simultaneous search.
So how do we implement this as a single function? Our enumeration function takes one number, n, which is like our step along that diagonal path.
Right, and for any given n, we need to figure out which word to test and for how long. So we use the reverse of a pairing function to decompose n into a pair of numbers, x, y.
Where x is the number of steps to simulate and y is the index of the word wy.
Precisely. So we grab word wy from our master list. We simulate our semi-decider m on it for exactly x steps. And if within those x steps, m accepts wy.
We found one. We output wy. It has been successfully enumerated.
But there's a catch. What if the simulation doesn't accept within x steps? What if it's still running? Our enumeration function has to be total. It must produce some output for the input n.
It can't just do nothing.
It can't. So if m doesn't accept within the allotted time, we have to output a designated word. This is a placeholder, a word that we know for a fact is in the set A.
So we only output the placeholder when our search for a new element fails at that particular step. But since the dovetailing process guarantees every actual element of A will eventually be found and outputted at some later step, the placeholder doesn't really hurt the final list, it just pads it out.
It pads the list, yes. The key is that every member of A will appear in the output, and every word that appears in the output is genuinely a member of A. And that is the definition of a recursively enumerable set.
That completes the connection. Semi-decidability, the ability to recognize, is mathematically equivalent to recursive enumerability, the ability to list.
There's one little caveat to this proof, which is a subtle nod back to the strangeness of undecidability.
What's that?
We need our set A to be non-empty, so we have a designated placeholder word to use.
And what if A is the empty set?
Well, the empty set is trivially enumerable, but here's the kicker. We cannot algorithmically test if an arbitrary semi-decidable set A is empty. The empty set problem is itself undecidable.
Of course it is.
So for this placeholder trick to be guaranteed to work, we have to sort of know ahead of time that the set isn't empty. It just reminds us that even inside this semi-decidable class, some fundamental properties are still elusive.
That is a perfect transition. We've mapped the recognizable territory, the RE class. Now we have to look at the true frontier of impossibility. Are there problems that are so hard they aren't even semi-decidable?
Oh,
Problems where we can't even recognize the yes answer, even with the freedom to run forever on the no case.
Yes. This brings us to the next, higher tier of impossibility. And let's start by looking at the complement of our anchor, the non-termination problem, HLT bar. The question is, will a given program not terminate?
Okay, so if HLT is semi-decidable, we can recognize termination, then its complement is HLLT bar. If we could build a semi-decider for non-termination, that means we could eventually get a yes when a machine is confirmed to run forever.
This is impossible, and we prove it using a really powerful result called the decidability test. It's a theorem that elegantly ties together the three computational classes we've been defining: decidable, which is REC, semi-decidable, RE, and the complement of semi-decidable, co-RE.
Let me see if I can state the theorem simply. A set is decidable if and only if both the set itself and its complement are semi-decidable.
That's it. It creates a perfect intersection. If a problem is decidable, it means both its yes case and its no case are recognizable in finite time. The mechanism for why this is true is really insightful.
The race analogy.
The race analogy. For any given input, we're going to run two separate semi-deciders in parallel, using dovetailing, of course, so neither one gets starved.
Okay.
Machine 1 is looking for a yes answer for the set, and machine 2 is looking for a yes answer for the complement set, M bar.
And since every single input has to belong to either M or its complement, one of the two machines must eventually halt and shout yes.
That is the stroke of genius. The winner of that race determines the final, definitive, total answer. If the machine for M wins, the answer is 1. If the machine for M bar wins, the answer is 0. And since one of them is mathematically guaranteed to finish, we've just built a total decision procedure.
So if a problem is decidable, it has to live in that perfect intersection of two recognizable worlds. The world of recognizing yes, RE, and the world of recognizing no, co-RE.
Now, let's apply that razor-sharp logic to the non-termination problem.
Okay. We know hey Paul T is semi-decidable, so it lives in ORI.
Right. Now, if the non-termination problem, hey Paul T bar, were also semi-decidable, if it lived in co-RE then.
Then according to the theorem, HL itself would have to be decidable.
Which we know is fundamentally false. It's our bedrock of undecidability.
It's a contradiction.
The necessary contradiction. Therefore, HLT bar cannot be semi-decidable. You cannot even recognize the set of programs that run forever. The search for non-termination is utterly and completely beyond the reach of algorithmic recognition.
Let's talk about another critical problem that's way outside the semi-decidable scope, the totality problem, or total.
Right.
This one asks, given a program P, does it terminate on all possible inputs?
Total is, in a sense, a step above even non-termination in its complexity. It is not semi-decidable.
And why is that?
Because the question requires you to check an infinite number of inputs. If a program P halts on the first input and the second and the third, and it keeps halting, how do you ever confirm that it halts on all of them? You can't simulate all inputs at once.
Intuitively, trying to prove a universal property over an infinite domain feels much harder than proving an existential one, like, does it halt on this specific input?
It is much, much harder. The formal proof shows that the set of all total computable functions, all the programs that are guaranteed to halt on every input, is not recursively enumerable. And since we just proved that recursive enumerability is semi-decidability, total has to fall outside the RE class. You simply cannot generate a list of all the programs that always halt.
So we really have these distinct layers of computational possibility. We've successfully mapped out a kind of hierarchy of undecidability.
We can visualize it as the map of undecidability. At the very bottom, fully contained and safe, is REC, the decidable problems, perfect certainty.
Okay.
Layered above that, we have two big overlapping circles. The first is RE, the semi-decidable class. This is where HL lives. We can recognize the yes cases.
And the other circle?
That's co-RE, the class of problems whose complements are semi-decidable. This is where the non-termination problem HL bar lives. We can recognize the no cases for halt. And the key insight from our theorem is that the intersection of those two circles, RE and co-R, is exactly the REC class.
If you're in both, you're decidable.
Exactly. But then there's the true King's class of unsolvability, the problems that lie completely outside this entire map, neither in air nor in co-R.
This is the highest tier of impossibility.
It is. And this is where we find problems that require these massive universal statements. The prime example is the equivalence problem, EQIV. The question is, do two programs, P1 and P2, perform the exact same computation for every single input?
So to be equivalent, for every possible input string, they must either both halt and give the same output, or they must both run forever.
Yes, because this requires checking two separate universal quantifiers, one over all inputs and another over the behavior of both machines. EQIV is just fundamentally harder than HLT.
So neither EQIV nor its complement is semi-decidable.
Correct. You can't algorithmically recognize when two programs are equivalent, and you can't even recognize when they are not equivalent. It's completely beyond our reach. Even if you were somehow promised that both programs were total, that they always halt, the equivalence problem between them would still be undecidable and non-semi-decidable.
That's incredible. So just comparing the overall behavior of two arbitrary programs is fundamentally beyond our algorithmic capability.
It is a core limit of computation.
Wow. Okay, that really wraps up our exploration of this gray area. We started by just accepting that not all unsolvable problems are created equal. And we've gone from that simple idea of one-sided recognition all the way to establishing the absolute limits of any algorithmic search.
The journey has really been one of mapping the boundaries of possibility. You now know the crucial difference between a guaranteed no and the infinite silence of a maybe never. You understand how dovetailing is this essential trick that mathematically connects seeing an answer to listing all answers.
And maybe most importantly, we have a clear map, a hierarchy of impossibility from the one-sidedly recognizable problems like HLT all the way up to these completely unreachable problems like equivalence. We have, in a sense, closed the book on the question of computability.
And with that map in our hands, we're ready for the next phase. We know what can be computed and what can't.
So what does this all mean? We now get to shift our focus entirely. We can stop asking the theoretical question, is this problem solvable, and start asking the intensely practical, crucial question that governs our entire modern digital world.
Assuming we can solve it, how expensive is the solution?
Exactly. How expensive in terms of time and resources? We transition from the question of can we solve it to the rigorous and frankly terrifying question of how long will it take? That is the realm of complexity theory, and that is where we dive next.